what's up to you all, grade 12 Mindsetters? Welcome to your favorite show, Learn Extra Live with me, AB, Abram, and John. We're here to learn more and learn extra. I hope you enjoyed your day at school. I wonder what were you doing on your physical science class? Share it with me later on the show. John, how are you?
I'm really good, thanks, Abram. Great to have you with us, grade 12s. I hope some of you are watching the grade 11s and you've enjoyed some of the bonding that we were talking about. I believe there's a great post on Facebook.
Yes.
Can I go and look at it? Okay, so for the grade 12s that missed the grade 11 show, here's the post from Shadrach. Shadrach's got the idea of using pup to make some bonds. So it's the coolest bonds ever as far. But I used marshmallows, so maybe I think that's sweeter, don't you think?
I'll try also cotton.
You think it's cotton?
Yeah.
I don't know.
I think that one, it's papa bonding.
It's papa bonding.
Yes.
Okay,
Very
guys.
creative.
We got, absolutely well done, Shadrach. If you're still watching, and what have we got in store for today?
Well, Mindsetters, we're all going to be bonding together on facebook.com/learnextra. If you're struggling, I'm here to help you guys. John and I are more than happy to take your questions. And also, if you see some other Mindsetters struggling on the page, help them. Share the page because we're all about working together this year. Another thing that you need to do is to download your notes, which are for free on learn.mindset.co.za. It's what John is going to be going over. So it will be more helpful for you to download them. And lastly, follow us on Twitter at LearnExtra. Since I've been stressing, John, that we are working together with the Mindsetters, we've got this awesome campaign.
Tell us about it.
This campaign, it says, work together. We're a team, Mindsetters, and we don't want you to be left behind throughout this whole year. So it's a campaign that we've started, and we're going to be with you up until the end, the last day of your exams, and even on the results day.
Absolutely. And guys, I don't know if you know, I'm going to ask AB to post it, but the matric final timetable is out. So you can actually start to set and count down the clock to when you're going to be writing your exam. No excuses anymore. You can get your exam timetable ready and gear up to the fact of when you're going to be writing physical science, when you're going to be writing maths, accounting, and life science, all your subjects. It's available. I'll get AB to post put up the post after this break. I've got it on my laptop. I'll just need to show it to him. But I really want to stress, it's never too late to start, and it's not too early to begin either. Okay? So you want to be ready for those exams, starting on the 28th of October, and they will end about the 29th or 30th of November. It's a shorter period of exam time. You need to get ready for it. Start working now, preparing for your term test that's coming up soon. And I'm sure organic chemistry is going to be a big part of that test. So let's not waste any time.
But one last thing before you scare the Mindsetters. Mindsetters, there's an awesome competition on the Work Together campaign. All you need to do is to look for the picture that is posted on Facebook, caption it, and get your friends to like your caption. The more likes you get, the better your chances of winning an awesome tummy takers a pair. But now John is going to be telling us about the challenge question also.
Okay, I just want to get to that photo because I think it doesn't make sense just to throw it out. No, let's get it. Abram's been posting lots. I seem to have missed it. It's further down. Let's make sure we get it. Okay, we'll make sure it's up at the top of the page just now. But talking about the page, there's your challenge question up at the top of the page. It's a bit of a flow diagram. Abram, please won't you post the other picture that goes with that? Because the flow diagram isn't difficult to read without that. So we need the picture, which I'm going to show the Mindsetters now. At the end of the show, we'll post the answer as well. So make sure you're there. And then the final little bit of a challenge before we really get into it is we're sitting 8 likes away from 69,800. Can we get there? I tell you what, if we can, maybe we can have 8 marshmallows each.
It's 798 now.
69, 798. Only 2 to go.
Yeah.
Brilliant. Okay, so you watch the likes. I'll watch the challenge question. We're dealing with reactions, organic reactions. Let's get going by giving you the challenge question this evening. So there it goes. gives you a flow diagram, shows compound A. Okay, now you won't be able to see this on the Facebook post until Abram gets that other graphic up. Compound A can be converted into 3 other organic substances. So there's compound A. I'm going to give you a clue just to help you, so because it's difficult to see. 1, 2, 3, 4 carbons, so it's C4, and they're all single bonds, so we know that that's H. How many? 8 plus 2 is 10, and 1 O. There's the O. So you know what that is, C4H10O, and recognize the functional group is OH. That should give away the clue of what its name is. If it undergoes dehydration, it makes compound C. If it undergoes substitution, it gives you 1-bromobutane. If it reacts with ethanoic acid, it gives you compound B. What I want you to do is I want you to give the IUPAC name of compounds A, B, and C. So we're starting with C4H10O. That's got an OH group in it. We're undergoing dehydration. We're undergoing substitution with, and that forms 1-bromobutane. And we are reacting it with ethanoic acid to form compound B. Please tell us what A, B, C are. A, B, C, the products. What are they? Okay, you got it?
I'm thinking AB.
Oh, you're thinking A, B. No, it's not all about you. Okay, just before we get going, so let's just quickly revise the different types of organic reactions you've got to go. Guys, what's on the board is in your notes. But I'm going to go through it quickly, and I'm going to try and illustrate stuff as well, just to make it very clear. So the first thing that we're going to do is we're going to say, you need to know about substitution. Okay? I want to illustrate for you substitution. Now, let's just mime it for a minute. Okay? Abram, I want you to watch carefully. Okay? So when we go like this at the side of a soccer field, then we're talking about? Substitution. Okay, so I'm going to do this, and we're going to substitute. Come, go to the board, and you see, now I'm over here, and see where Abram is. Okay, so we've substituted. Come, we better change over. Okay, so there we go. There's substitution. The one takes the other's place. We need to be very clear about substitution. It's a very common reaction. You need to know the conditions for substitution, and you need to recognize that one atom is substituted with another group of atoms. So substitution occur with single bonds, so we can take a hydrogen and replace it with a bromine or a chlorine or something like that, or with a group. We can take off a hydroxide and put on a halogen as an example. So the list of substitution reactions are given over here, so we can have alkanes and halogens, and you need to recognize that we need sunlight and heat to make that. We get alcohols and haloalkanes. The products will be the haloalkane, or this is the, sorry, it wasn't a haloalkane, but it's an HX. It's like an acid, hydrogen chloride, hydrogen fluoride. You'll get the haloalkane and water. This happens when you've got primary, secondary alcohols, and you need high temperatures for that. And when you've got haloalkanes and water, and you use potassium hydroxide or sodium hydroxide, you get the alcohols being formed. So it's the reverse reaction. You have to dissolve the haloalkane in ethanol, and you've got to heat it. So please be aware of these reactions. Okay, substitution, critically important. But my favorite one, and the one that I really love to show, is addition. Now, it's not because some people can't add that we're going to do this. And even without a calculator, talking about adding, what are our numbers like? Come, what are our numbers on the page?
It's 69,789 and 98.
98. 98. We want 2 more people
Actually,
to like.
it's 802 now.
802. Well done, guys. Now we're wanting to push to get to 70,000. Only 200 to go. Okay? So let's keep it up. Guys, addition. We want to add properly. So we're starting with a molecule that is not saturated. Very important term. I'm going to talk about it, and I'm going to illustrate it as well. And hopefully we can get some space over here to do this. When something is saturated, give you an example, methane. Carbon always has 4 bonds. They're all single bonds, then it is saturated. It has the maximum number of partners. Around every carbon, there are 4 other atoms. So in total, we've got 5 atoms. Carbon's the central one. We've got 4 bonds. They're all single bonds, single covalent bonds. And from grade 11, you should remember that when you've got that, it will be a tetrahedral shape. That you don't need to know for the exam, but it just makes sense when we're explaining it. But now you get an unsaturated scenario. And I want to show you what unsaturated. Unsaturated means the following. It means there's a smaller number than the maximum. So we could have something like this. Let me not jump. I want to arrange it properly. So there we go. We could have something like that. Now, count the number of bonds that we've got. Around this carbon, there's 1 bond, there's another bond, there's another bond, there's another bond. Now, just because I've drawn over in pink, don't think it's an extra bond. That's 4 bonds. And around this one, 1, 2, 3, 4. It's also got 4 bonds. So we've got a maximum number of bonds. We haven't missed out a bond. But how many partners have they got? Look at this carbon. This carbon has got 1 hydrogen, another hydrogen, and a carbon. So how many partners it's got? It's got 3. It's got 4 bonds, but 3 partners. It is unsaturated. It hasn't got the maximum carrying capacity. It has room to take another something on board. So we can add to unsaturated substances to make them saturated by breaking a bond. And I want to show you what that is. Abram, will you come and help me here? I'm going to my desk, and I just need to get a drink of water. So, here is my little molecule. You're going to have to hold it for me for a second because I need to do something. Guys, look at it. It's exactly the same diagram or model as the diagram that I drew on the board. We've got 2 carbons over here, and these white marshmallows are the hydrogens. There's the hydrogen, there's the hydrogen. Notice they're all in one plane, and they're quite nicely spread apart. Now what happens is I want to get another hydrogen in there. I want to make an extra bond. So I'm going to reverse a process that I did earlier. I want to break this bond, and I'm going to take the double bond, and I'm going to break it. Okay? And look what's happening. It lifts up like this. And imagine now that I've got an extra space for something to fit onto. And I'm going to fit it on like that because I'm not a magician. I'm going to just push it in there. And it looks a little bit messy. And it probably is for a while until these molecules arrange themselves so that we get them into that sort of shape. And stereo in space, they arrange themselves so they're as far apart from each other. Okay? So I've broken the double bond and I've added an extra hydrogen. Notice now, I started with 4 hydrogens. Now I've got 3 hydrogens on this side, 3 hydrogens on that side. That's 6 hydrogens. This is an example of addition. Happens every time. We start with an unsaturated molecule and we ended up with a saturated. Notice, 1, 2, 3, 4. 1, 2, 3, 4. Saturated. Maximum number of partners, maximum number of bonds. Okay, thank you. Do you want another marshmallow?
Thank you, John.
Okay,
Reward.
right, guys. I hope you've got that. Let's go back to the board and think about how we're going to do this. Okay, so while Abram's taking his marshmallow, we say addition reactions occur when an atom or a group of is added to an organic molecule. So there's adding. These take place when a double or a triple bond is broken. Now, we didn't show the example of the triple bond, but it's very easy to see. You can play with pup and sticks or with cotton wool and sticks and show the breaking of the double bond. The examples in the notes are given here, and it's a very nice summary. We can get hydrohalogenation, where we're taking an HX and we're adding it to alkene. There's no water that's formed. We're forming one product in addition. Very easy to see. You start with two things, you end up with one thing. You always have one product with addition. Halogenation is where we take an alkene and we have the alkene adding. We get hydration, we add water, and we get hydrogenation, where we're adding hydrogen. Guys, please go over each of those. In the exam, make sure you specify that it's not just addition, but it's hydrogenation or hydrohalogenation or halogenation or bromination, something like that. Now, the test for saturation is to see if you can add the gas or the organic solvent to bromine. If it changes color from orange-red to a colorless solution, then you know that you started with an unsaturated substance. If it was saturated, it would not change color unless it's placed in sunlight. Last thing that I want to deal with is elimination. Now, elimination reactions are reactions in which a smaller molecule is removed from a large molecule which is produces an alkene or another molecule. So dehydration is an example, and we will show some of those. Thermal cracking, breaking up, catalytic cracking, and as I said, you can go over those. Basically what we're saying, large molecule, break apart into two. It's the opposite of addition. Okay, Abram, I think we've done enough on our summary.
Let me eliminate you, John. For now, it's my chance. Mindsetters, make sure that you still stick to us on Facebook.com even during the break. Help other mindsetters. I see Sharon, I see Mukove on the page. Guys, you're doing a great job. Keep it up. We'll see you after this break. Welcome back, awesome matriculants. Send your questions through if you're struggling. We're here for you, and I see a lot of mindsetters that are helping each other on the page. It's good, guys. Keep it up. That's why we're working together on this journey. John?
Abram, thank you so much. Guys, I hope you're ready to get into the Improve Your Skills questions. These are exam questions. You need to be checking that you can do these. So let's make sure that we've got them. We've had a technical glitch with the flow diagram for the challenge question. Just got out my laptop, and Abram will be getting it shortly, so just hold on for that diagram. Okay, so let's revise and let's go over what this is. Some organic reactions are shown below, so let's just make sure we've got them. Let's use a nice bright color, and I might need to just go over this diagram. We've got X over there. We know that there's Br2 in UV light, and it gives us 1 bromopropane. Okay? That's the one thing. Then we've got propanol, and 1-ol, and it forms bromopropane, 1 bromopropane. We've got prop and 1-ol over here, and we've got concentrated potassium hydroxide and heat, and we make Y. Now, the alarm bells should be ringing. You should be remembering exactly what we've done, because we've mentioned all of these reactions in our little summary. So let's make sure that we can name the reactions illustrated by A, B, C, and D. So first of all, let's start off with A. So when A goes from X, and we don't know what X is, but we've given the clue that it's bromine that is being used, and we make one bromopropane. One bromopropane. It's not saying this is the whole reaction. Okay? It's just saying it's one bromopropane. Now, be very careful here. When you've got bromine in UV light is essential. That will only happen when you have got substitution. So A is an example of substitution. And what are we adding? We are adding, you don't need to do this, but we are adding a bromine atom. Please notice that it was just adding one bromine. If it was addition, then we'd have to add two bromines across a double bond. But at this stage, I reckon that we've got substitution there. Next one, number B. We start with propanol, propan-1-ol, and we end up with one bromopropane. So notice it's the number of carbons hasn't changed. This one was C3H7OH, and this one is C3H7Br. Can you see that what's happened is that? So what do you think has happened? That what we've gone is we were OH, and now we are Br. What do you think? I think it's substitution. So number B is also an example of substitution. What did we substitute? We took out, we removed the OH, and we changed it for a Br, just so that you can identify what's happened in that point. But now, we're not writing the chemistry there, so please don't get upset when I said Br. Br can't be on its own. What about number C? It's gone back to being OH. So what have we done? We've taken the Br and we've replaced it with an OH. So again, number C, it's substitution. And in this case, it's the reverse of what we had there before. We started with the Br, we started with the bromine on that end, and we've replaced it with a hydroxyl group. Okay, we've replaced it with the hydroxyl group. And the last one, A, B, C, and D. So if we take concentrated potassium hydroxide and we heat this, yes, you're going to do substitution again. So all of them are examples of substitution reactions, and we're replacing those things. Use condensed structural formula to write a balanced equation for C. Now, reaction C was when we went from the 1-bromopropane to the propanol, propan-1-ol. So let's make sure that we've got it right. So we've got prop is 3, and we want condensed structural formula. We don't want to misread the instructions. So we must not just write the molecular formula. Remember, this formula is a molecular formula. We don't want that. We want to show the bonds, but we're going to show the hydrogen bonds there. We're going to show that there are 3 hydrogens over there. Remember that that's one end. Then we're going to do 2 hydrogens over there. We're going to do a hydrogen over here, plus there are 2 hydrogens over there, plus the bromine. So that will give you your condensed structural formula. I could have drawn them a little bit closer together, but I didn't, and perhaps I was wrong with doing that. Then with C, we want to get to OH, taking its place. So what we can do is we can simply say, let's take hydrogen and water, in other words, and we're going to say H2O. Now, because it said condensed structural formula, I don't think I need to give the whole thing. I can do it like that. And what I'm going to end up with is H3C, CH2, and CH2. And here's the important thing, OH plus HBr. So there we go. We've got a substitution taking place. It's an example of a hydrogenation using the water. Okay, write down the structural formula for compound X. Now, let's have a look where X is. It's up over there. Now, what I said to you originally, it's adding one bromine. So the structural formula must have been without the bromine. And it's likely, but they haven't told you, but because of what I think it is, I'm going to say that it would be in hydrogens, most likely to be the hydrogen just simply there. So if we take a look at it, in UV light, it's just the alkane, so it's likely that this is an alkane. So we're going to say C3H6. Write down the structural formula. Structural formula must show all the bonds, and that means C3, not H6, but H8. Okay. In order to obtain product Y, okay, let's have a look at that 1-bromopropane. Product Y is this one. What it tells you, it was heated with potassium hydroxide. So it's heated with a concentrated solution under reflux, used condensed structural formula to write a balanced equation for the reaction. Now, again, we need to get balanced equation with the structural formula. This is a little bit tedious because it's all the structural formulas. Condensed structural formula, CH2Br. Now, when we add in the potassium hydroxide, we're going to show it like that, and do the balanced equation again to balance it. We're simply saying that hydroxyl group is going to take the place of the bromine, and we're going to get KBr as one of the products. Last one for this question. It says a group of learners decided to heat that with sodium hydroxide instead of using concentrated under reflux. Write down the IUPAC name of the organic compound that they'll form. So now they're using dilute sodium hydroxide, and they're heating it as well. So we want the IUPAC name. Guys, you've got to remember the substitutions that are happening here. So let's just go back to our summary notes and make sure that we've got these correct, and so that you can be very clear that you've got them sorted out. So notice here the haloalkane plus water plus potassium hydroxide. We've got to dissolve it, we've got to heat it, and what we're going to form, we're going to form the alcohol plus the HX. So let's apply that knowledge. It's a different reaction, we're using different products. We're going to form the IUPAC with the alcohol. So over here we've got C. Let's just draw the molecular formula, C3H7OH. Now, if we want to get the IUPAC name of that, draw the structure out. We've drawn it a couple of times already, and you'll see that it's not too difficult to get that. It's prop and 1 ol. Okay, the position of the OH obviously depends on the bromine. And if it's in a different position, the bromine's in a different position, then it could become a secondary alcohol, meaning it's in the middle of the chain. Right, let's move on from there, and let's have a look at the next question. It says most organic can undergo substitution or addition or elimination reactions. They produce a big variety. There are some incomplete ones over here. So reaction 1, reaction 2, reaction 3, and we can have a look at that. Name the type of reaction represented by the third one. So here we've got reaction number 3. We're given something that's got a hydroxide, hydroxyl in it, and it's sulfuric acid and heat. Sulfuric acid is an amazing acid, but it's a very powerful oxidizing agent as well as a very powerful dehydrating agent. In this case, it will undergo dehydration. So what that means, it's going to remove that hydroxide, and it's going to take it away, and a double bond is going to form. It's going to take that away, take away hydrogen from there as well, and we're going to get a double bond. So make sure that you understand that. It's an example of an elimination reaction. Good. Move on. Both reactions 1 and 2 are examples of addition reactions. They've told you that. Name the type of addition that is represented by each. So let's go back to it and have a look at it. What are we adding? In this case, we're adding water. If we're adding water, then it's hydration. And when we're adding HBr, that's hydrohalogenation. Okay, so when you add water, hydration, hydrohalogenation. These are both additions. We must give the specific name. So I've written that down. Then it says, write down the structural formula and the IUPAC name of the major product of reaction 1. So the major product of reaction 1, where we're getting the hydration, we're going to add in. Now notice that the double bond is in position number 1. We're going to break the double bond. We're going to add in how many carbons were there? Sorry, I didn't see that. It's CH3, CH2, CCH2. So that's 4. So I like to draw the structure, 4 carbons like that. And we are going to get the CH3. That's not going to change. The structural formula. Put in all the hydrogens. That one. And now I'm going to put in a hydrogen over there. Now this is where you need to decide. Those are the hydrogens. We've broken the double bond. So where is the OH and where is the hydrogen going to go? We've got to add a water, an OH, and the hydroxyl likes to go on the end. Just like that. It's got more space on the end of the molecule. Doesn't like to be crowded out. And we've written the structure. Now we need to give the name. 1, 2, 3, 4. So 4 is bute, and it's an-1-ol. Okay. Last question that we can manage for this one. Let's just do this one. Reaction 1 takes place in the presence of a catalyst. Write down the formula of the catalyst used in reaction 1. So the catalyst for this, you know what, Abram? I'm sorry, yes. I've gone blank. Mm-hmm. I'll have to get back to the learners after this break.
Let's
have to go and look it up. So let's take a break now, and we'll see you after the break.
Awesome. If you're struggling and have some questions, throw them on facebook.com/learnextra, inbox me, or post them on the wall. See you after the break. Welcome back, Mindsetters. Now, if you haven't downloaded your notes, go to learn.mindset.co.za. That's where you get all your notes for your favorite subjects. But I have the link posted also on facebook.com/learnextra. The challenge question is on Facebook. So, Mindsetters, we also have the diagram that is commented on that post. So make sure you check the diagram and then give us the answer to the challenge question.
Excellent. We're going to go and do that challenge question now. But before I want to just wrap up that last question. The memo says that it's sulfuric acid, that you would need to add concentrated sulfuric acid to act as a catalyst. Usually when water is involved, sulfuric acid is a good catalyst. Normally it acts as a dehydrating agent. In this case, it's helping the addition process to add in and make that alcohol. But let's have a look at our challenge question. So it's again quite similar to what we've done before. It gives us a flow diagram, and these are quite popular. So let's break them down as simply as we can. So the first thing is we're going to start with this substance, compound A. And I gave you the molecular formula. I'm now going to give you the name of it. Let's count the number of carbons first of all. 1, 2, 3, 4 carbons. So 4 carbons is bute and 1 ol. And the ol because of that bit there. So it's bute and 1 ol. And what's happening? It's undergoing dehydration. Now, this is also the answer to question 2.5 because that dealt with the same sort of reaction. When we get dehydration, we're not adding water, we're taking away water. Then what we're recognizing is we're going to take that OH away plus another H, which will give us H2O. That means that compound C is going to be a double bond. So there's an addition reaction taking place here. Addition. And that means that compound C has got to have a double bond. Has a double bond in position number 1. So it's bute 1. Double bond means ene. Okay. So bute 1 ene, that's a molecule number C. What about the next one? Number A we've given that. We've done number C because that was quite easy. Now we've just left with number B. So here's something that we haven't done this evening. And it's one of my favorite sort of things to do. We're going to take an alcohol, bute and 1 ol, and we're going to add ethanoic acid to it. Let's have a look and see exactly where that is. We're going to draw the structure, bute 1, 2, 3, 4. We're going to put the H over there, the OH over there, always with an OH. Make sure that there's the bond between the oxygen and the hydrogen. Even if the old exam papers don't have it, we need to draw it in. They want to see that bond. There's your butanol. Okay? And what we're going to do is add that to ethanoic acid. Now I'm going to start with the functional group. The functional group is the O, and we're going to get the OH over here, like that. And it was just eth, so it's like that. So it's just 2 carbons. Let's extend that and see now what happens. When you get an alcohol plus a carboxylic acid, you form, when you add the presence of sulfuric acid and perhaps even a little bit of heat, you form an ester plus water. So how does this thing actually happen? And it's very interesting that it's those things that combined. That gives you your water, and these join together. So let's draw that new structure, and the new structure will be 4 carbons in a line, then an O, then 2 carbons, the O there, double bonded O. Now we just fill in the hydrogens. And there we've got it. We're almost done. We've just got to name it. So the structural formula is drawn. Please remember that if you were writing a balanced equation, you couldn't leave it there. You'd have to write HOH. They asked you to draw the structural formula, and it's not in a straight line. Now, how do we name this? 1, 2, 3, 4 from the alcohol side, and 2 from the acid side. So the name of this is butyl ethanoate. Now, we've normally written it like that, but I believe that it's not incorrect if you join these together. Although I've always drawn them separately, apparently there's now a sense that you can write them as one word. Butyl ethanoate. Got it? No spaces, even though that's been the tradition to write it like that. Plus water, that's obviously there. Okay, so this process is known as esterification. It's one of those reactions of organic that is very interesting, and it's very nice to do because it gives you very fragrant aromas. So I think we've answered the challenge question. Abby, some questions from the learners.
Yes, sure. Let's start with this one. Lineage to niche. What is the difference between C3H and C3H?
Okay, let's have a look. C3H what? C3H isn't a molecule. It could be C3H6, or it could be C3H8, or it could be C3H4. This one, C3, when it's double, it's of the form CnH2n. Okay? Now, if you've got that, then you know that you've got an alkene. That's got one double bond in it. This one, this is of the form CnH2n plus 2. That's an alkane. It's saturated. I'm going to make a point of saying this is saturated. They're all single bonds here. And this one belongs to the family of, let's write the general formula, CnH2n minus 2. This belongs to the family called the alkynes. And it is also unsaturated. So the ones in green are unsaturated, where this one is saturated. I hope that answers your question. Was it Leonard? Okay.
It's Lech.
Huh?
Lech.
Lech. Okay. So please remember that. Make sure that you understand from the general formula the homologous series called the alkanes. To name these, we'd know that this would be propene, and I would prefer you to actually put the number in, although it's not essential. This is propane, and this is propyne, just using the IUPAC naming. Okay, next question.
Okay, Katlawa says, I'm a bit confused on how do I identify whether it's a substitution, addition, or elimination reaction. Please help.
Okay, very, very good question. And I'm going to try and assist you as much as I can. Okay, I'm going to start with addition, because for me, addition's easiest to work with. And I'm going to do it like this. In fact, let me do it diagrammatically, and maybe that will help you. So I'm going to choose a little triangle to represent something. So let's have that as a triangle. Okay, if you've got a triangle, plus let's take this and let's change the color, and let's make that the color, and we do that. Now, addition says to me the following. If I take those two and I add them together, then what I'm going to get is the following. And just give me a second, because this is all a little bit on the spur of the moment. So we're just trying to get it right. We get that one, and we're going to get that one like that. So what do you notice? We started with how many reactants? We started with 2 reactants. So this is usually the organic stuff, and this is the thing that's going to be added in. So you've got 2 things, 2 reactants. And what have you ended up? You've got 1 product. And that is probably the easiest way to identify addition. The other way is to recognize that this thing over here must be unsaturated. Okay? That must be unsaturated. And at the end, this one will be saturated. In other words, it's like what we started with, breaking the bond. Do you remember the marshmallow model? We broke the bond. That's exactly what's happened. We've added things to it. That's the addition reaction. Now, let's do elimination next, because it's actually very similar. But I want to show you what's different. Elimination says that we're going to start with that thing. Okay? We're starting with that, and what do we end up with? Well, you guess. Abby, what do you think we're going to start with? If we start with that picture, what do you think we're going to end up if we're doing elimination?
The same picture.
The same thing, exactly the same.
Yes.
Now, elimination means breaking apart. So what are we going to end up with? We're going to get...
separately.
Yeah, that's exactly it. So let's just do this. It does help if that selects properly. We're going to get that and that as separate things. Okay? So please notice what the pattern is here. The pattern is that we started with 1 reactant and we end with 2 products. Again, over here, this could be, it doesn't always have to be, but it is the reverse of addition. So in this case, we could start with something that is saturated, and we end with something that is unsaturated, because the double bond reforms. Doesn't always happen, but it can happen with elimination. Elimination, we're taking something off, and sometimes we're forming the double bond. Okay, substitution. Can you get the picture? Can you see, can you predict what the picture is going to be? Well, I hope you can. I hope you're drawing something for yourself. Let me start with the triangle again, and I'm going to pick that triangle, and I'm going to pick that. I'm just going to pick it and pull it down, because I'm going to change it in a minute. I want something else as well. So let's say we've got that. It's different to one of the others that we've had before. I don't want you to think they're exactly the same. They're not the same as what we had before. So what we've got is that sort of picture, and what we've got is another thing. Let's take that block over there, and what we're going to do with substitution is something like this. Let's take the triangle. Let's move that one. There we go. And all that happens in substitution, so we start with two slightly more complicated things. We add those together, and what do you think we're going to get? We're going to get an exchange. So what will happen is, instead of it looking like that, we're going to get this thing, and I want to just copy it so that I can paste it onto the page, and then I'm going to change it. I want to paste it, pull it over here, and let's copy this, and let's paste it. Oops, don't rotate it, please. And now what's going to happen? We're just going to swap partners, and that's substitution for you. Okay, so they've changed fundamentally. They were two different things. They've just swapped over parts. So where the triangle was with the circle, the triangle and the triangle are together now, and where the triangle and the square were together, or rectangle were together, they've swapped over. You need to know the conditions under which substitution takes place, and you need to know the rules of substitution to a certain extent. I know that in previous exams there were things about Markovnikov's rules. Those are not mentioned directly in caps. So please don't get hung up about mechanisms. They're usually going to keep them quite simple so that you are very familiar with what's happening. Okay.
Okay, last question. Banela says, in compound C, why did our double bond go on the first carbon? In other words, do we always put in the first carbon? Please help me on this section. It is difficult.
Okay, so was this for the challenge question?
Yes.
Okay, so it's a very good question, but I just want to illustrate it very quickly by doing something that's slightly less complicated. If I have OH there, because I haven't got time to draw on all the H's, what I want you to see, I'm just using the propanol, not the butanol. So if that was propanol, okay, what we're going to do is we're going to take out this OH. Where was the OH attached to? The OH was attached to that one. And where's the next closest H? Well, the next closest H is over here on carbon number 2. So what happens when we've got that sort of arrangement? We've taken out OH, we took OH, and we took H, and it's made water. What's going to be left over is these two. What's that going to do? It's going to make a double bond. I think we all agree with that. So I'm going to take that away, and I'm going to replace it with the double bond, and just make it in like that. Can you now see that this is on where the OH was? That means that has to be carbon number 1. If I was a very long molecule and the OH was in the middle, then it would be where the OH was, closest to the ends. Okay?
Yes. Thank you so much. Thank you so much, John.
Guys, I just want to say thank you so much. Please check the page out. On the page, you will see the number of likes that we're at, the challenge questions, and the answers will be posted shortly underneath there. And the techie, the walk together poster will be up in a few minutes. So comment, like, get yourself involved.
Thank you so much, Mindsetters. It's been a great evening, and we love what you've been hearing on the page. You guys helping one another, and also sending your questions, and John helping you guys. Without you, we wouldn't have done this. But otherwise, keep on being a mindsetter. Like our page on Facebook, which is facebook.com/LearnExtra. John, thank you so much. It's been a great and fun show. I've learned a lot, and thanks to the Mindsetters, we're now at 69,844 likes. And
brilliant. That's more. That's really good. Going.
Big ups, Mindsetters, and learn more, learn extra from me. Last words are keep on being a mindsetter. Peace.